So we have been talking about boundary value problems. Okay. Okay. Especially second order ODEs. Okay. And we have talked about both linear and nonlinear kinds. Okay. And we have talked about techniques. The techniques that we have talked, one is completely based on finite difference approximation. Okay, of derivatives. Second technique that we talked about was the shooting method. Okay, and what is different or what is unique about this technique is that it tries to solve BBP using IVP methods. Okay, so solves boundary value problem using let's say well developed high accuracy, highly accurate, or methods which are more accurate methods to for mutual benefit. Okay. Okay, so well, there are like a whole range of techniques, right? I'm just giving you a flavor, different approaches that you can actually. So when you can devise your own method, right? But I just want you to know about like what are the very important approaches people have taken, right, in devising methods. So the first one was, of course, based on finite difference of relative terms, right? And then you get finite difference equation that will lead to a matrix form that will lead to a matrix equation actually. Okay, and that you can solve. Okay. Tutti method, that's a completely different approach again. And third approach, this will be the whole last approach in this boundary value problem that we'll discuss. Okay, but that's actually that is a very important. There's a very important idea which is utilized in this third approach. So what is done is, so instead of looking at the equation, what you do is third approach is you approximate the solution itself. You presume a solution. Okay, approximate, or you can, I should not say approximate, you can presume a form of the solution. Presume that the function which satisfies the differential equation is given for the okay. Is already known in certain form. Right? Already known in certain form. What do you mean? See, if I know the answer, what is the need of doing all this exercise? So well, so it's known and it's still not known, right? What is it? What is it that is not known? So you are going to do is you construct a function which will have some unknown parameters. Okay, so this function will have unknown parameters, which I need to find out. Okay, all right. So basically, um, what you're saying here is so there's a very important idea that I want to discuss here. That idea is basically treating functions as vectors. Okay. It's a very important scheme of mathematics called linear vector spaces. Okay, so it's an important topic in maths. In the beginning, people thought that, but the idea is that functions can be treated as vectors. Okay. So, so what does that mean? Well, remember functions are bunch of values. Right? So if I'm saying sin x, or if I say fx equal to x square, okay, actually I'm referring to bunch of values which go like, if I have x going from 0, 1, 2, 3, 4, I'll have values like 0, 1, 4, 9, etc. Okay. So if I have bunch of values, this is like a vector. Like that is the reason you can treat a function like a vector. Okay, and uh, and vectors. So then what is done is, uh, and the dimensionality of this vector would be basically based on how many points you're looking at. Okay, so that will be the dimensionality of the vector. So if I have, let's say, if I have x grid x line on which I want to have a function, and it is like let's say 4 points, 5 points, 6 points, that would be the dimensionality of the corresponding vector of x. So that would be, so the finer the, if you go to continuum limit, it becomes infinite dimension. So in that case, so finer the points, more will be the higher will the dimensionality, and continuum limit, that is just a jargon mathematicians use. Okay? The continuum limit, this function is like an infinite dimensional. Okay. What is important about this is what sometimes you get to see the curves like infinite dimension, so it's very difficult to understand what is meant there. So it's nothing, just a function with values specified continuously across the argument. Okay? All right. So now, what is important here is the idea that a vector. So in three dimension, the vector that we know in conventional sense, okay, what we know, for example, position vector can be, for example, it can be decomposed into its can be decomposed into its components, right? So there are always so you can, in a three-dimensional space, for example. So 3D space, I have a I have a position vector. Let's say position vector in 3D space. I have three components. Basically, I have three vectors. Right? That's why it's a three-dimensional vector, and it has a physical meaning in this case. So the physically, we all know that this vector can be decomposed in terms of I, j, and k. Okay, these are the basis vectors. Okay, so these are the unit vectors in terms of which you can write down by any arbitrary any arbitrary vector. So this is the vector v, so this is vx and vy and vz. So v can be written as, we all know that, vx I cap plus vy j cap plus vz k cap. You all are aware of this. The same idea is actually applied to functions when treated as vectors. Any function can be written as a linear combination of some set of basis vectors if there are n-dimensional space. Okay, if you choose n unknown values, and so a function defined at n discrete points, okay, the function value is defined at n discrete points, can be written as linear sum of n basis vectors. Okay? The function can be written as a linear sum of, let's say, n basis functions in n-dimensional space, meaning that it has n unknown values. Okay? So basically, function defined as at n discrete points. Just imagine that. So when I say n-dimensional space, I would mean that function has n values which can change independently. Okay? The function can. Okay. All right. So now, so what are these basis functions? That is, so like here I had direct basis vectors. So similarly, the function can be actually here I could break, so this position vector could be decomposed into three individual vectors, okay, which are parallel to these vectors, okay. So this vector is parallel to I cap, j cap, and k cap, etc. And so you decompose it. So this is essentially vectorial decomposition. Okay, you are actually, it's basically divide and rule kind of thing, right? So you first decompose into something which is easily understood and which can easily be treated, which can easily be analyzed. So you know what is, since you know what is x direction, so you basically think in terms of the respective components, and any operation done on this is equivalent to doing independent operations on all these three quantities, and then resultant will be summed up. So that is like linear superposition idea, right? So that is what. So this basically that makes our life easier. You can basically talk in terms of those constituents which can be easily handled. Okay. These are the constituents which can be easily handled, and then net would be basically when you have to do some operation on V. You imagine doing them individually on these three first, and then finally you add the net result. Okay, so that is the idea. Simply applied over here as well. So a function is decomposed into n basis functions. Okay, that means that there are basis functions which are there, which are there actually. Okay, so in n-dimensional space there would be n basis functions. Okay, so in ND space there would be n number of basis functions. Okay, I'm not going to the mathematical rigors. Yeah, I'm just giving you the basic, simple and physically appealing, physically intuitive, physically appealing ideas which are basically applied in mathematics, and the problems are trying to which we try to solve. Okay. Okay. So these basis functions I'm going to call phi, okay, x, okay, and there will be n of those. While I'm going to call like phi 1x, phi 2x. They are functions, okay, and up to let's say phi 1x. So in general, I have phi kx, okay, k ranging from 1 to, okay. All right. So um, so I'll just give you one very simple example. So for example, suppose I have a function that may look like, let's say, something like this, some arbitrary function. Okay. What you can do is you can imagine, you can think of, like, for example, let's say I'm going to, let's say I'm going to, well, let's say I'm going to divide this region, okay, in first just these two in terms of just I'm going to say that I have values known at x1 and x2. Okay, okay. So what you can do is you can say that fx can be written as, okay, fx can be written as simply a polynomial which is linear. Okay, you can approximate that. That is the first approximation, a linear polynomial, something like this. Okay, which is line, actually, a linear function of x. So fx would be equal to ax plus b. In this case, fx you are approximating by ax plus b. Okay. Now, so what you're doing here is, now I can write this as a times x raised to 1 plus b times x raised to 0. Okay. So what you're doing here is you're identifying x1 and x0 as your basis functions. Okay. All right. So I have I have 2 points. So I have two basis functions here. Okay. I have 2 points at which f is known. So it's a two-dimensional vector. Okay. At the moment f in my representation, in my discretization, it's a two-dimensional vector. Therefore, I will need two basis functions, and those would be x0 and x1. Okay. Suppose I decide to make finer, and let's say I'm going to have it's x2 and x3 here, x1, x2, and x3. So these are the points at which function values are known. Okay, then I'll have three. I can write down. I can approximate the function in this range by probably a parabola. I don't know how that's going to look like, but some kind of parabola, okay, which would be, since you have actually discretized to a finer one, okay, your error would be less. So, uh, so let's say the parabola might look like okay. So that would correspond to, I have three points, okay, and in this case fx would be written as ax squared plus bx plus c, okay, and your basis functions are nothing but 1 x and x squared and so on. So you take more finer points, more and more points, and you can actually approximate your function with their higher order polynomials. Okay? So when you express in terms of polynomial, when you try to approximate a particular section of a function in terms of polynomial, all you're doing is essentially you're basically defining so polynomials. So basically when you're expressing or approximating, is a better word, not expressing, approximating a function using a polynomial, okay, you are essentially, you are defining essentially the basis functions, which are 1 x squared, x cubed, etc. Okay. These would be your basis function. If you decide to, should you decide to go to express your function in terms of polynomial as a polynomial approximation, then in that case these would be your base. These are basically nothing but the basis functions. Okay. But remember, like in 3D, there is not a unique basis function. There can be all different kinds of basis functions. IJK need not be the only way you can represent. Okay, there can be other kind of reference directions in terms of which you can show a position vector. Similarly, you can have a bunch of different kinds of basis functions, okay, and which basis function to use, that is where the trick lies, okay. So we'll come to that, but let me first elaborate more upon the basis function. So these would be your basis functions. So basically you can say that phi 1x is 1, phi 1x is 1, phi 2x is x, and so on. Phi 3x is phi kx would be x raised to k minus 1 and so on. Okay, so these are the basis functions that you can construct, and when you try to write down a function in terms of these basis functions, you're not doing nothing but trying to approximate the function or the trend in function you're trying to capture by a best polynomial. Okay, so that would be your that is basically uh, yeah, yeah, that's right. Yeah, yeah, and then third order will be n plus 1 basis functions, right? Because including this x raised to 0 is also 1. Correct. Okay. So yeah, but remember that I have, if I have 3 points, I have second order polynomial, which is 3 degrees of freedom. Therefore, three basis functions required. Okay. So okay. All right. Any other question, Amit? Is that okay? I don't. Are you confirming something, or you have a question? What you wrote is correct. Okay. But do you have any specific question, or you're just trying to confirm something? You are unable to put the question, then what can I do? You have to ask me the question. What do you mean by? Please, I let me. Let's. I'll try to help you to put the question. Okay. What is it that is confusing you? There's something that is bothering you. So let me just, maybe if I write it over here, let's say if you are n, so let's say function defined at n points, function values at n points. Okay, that would imply n minus 1 degree polynomial. Okay, and therefore n basis functions, which is consistent with, because I have n points, so I have to have n basis functions. If I have two points, I have a linear function, first order polynomial. If I have a two points, first order. If I have 3 points, I have a second order, which is parabola, and so on. If I have n points, I have n minus 1 degree polynomial, and therefore I'll have n basis functions. When we get any equations to solve them, why you get extra basis and in this case? When we have n variables, we get n. No. Here I have, well, I think the confusion is arising because what do you mean by the degree of the polynomial? The degree of the polynomial is the highest power in x, I guess, right? So that is equal to, so if highest power is x is n, there are actually, so well, I think that is the source of confusion. So the question is, when we have n variables, we get n equations to solve. Here also the same thing. You have n points and you have n basis functions. That's it. These are, and then the way you call a polynomial n is n minus 1, because the way you define the degree is basically n minus 1. That's the way you define the degree of the polynomial. But it has nothing to do with the degree of the polynomial. You have n points, you have n basis functions, which is basically 1 x squared up to x to n minus 1. Okay, the n polynomial, and therefore this is a n minus 1 degree polynomial. So that sorts of the question. Yes, no. Okay. So yeah, so again, for others, maybe if they are having this doubt, I have n points, I have n basis functions. Okay, there is no confusion about that. And if I choose those n basis functions to be 1 squared and so on, n of them will end up at x raised to n minus 1. And if you construct a polynomial, these functions, that will be n minus 1 the order polynomial. Okay? So that's why if you have n points, you are actually approximating it using n minus 1 degree polynomial. Okay, so therefore 2 points is like your first order line, so 3 points are parabola and so on. Okay, all right. So what you do here is basically any function you write, that would imply I can write down any function as a linear sum of these a times a, sorry, so a1 times phi 1 plus phi 1 of x plus a2 times phi 2 of x plus a3 times phi 3 of x and so on. Okay, so that would be written as a linear sum of all these. This is like nothing but a1 times 1 plus a2 times x. Okay, a1 times 1 plus a2 times x plus a3 times x square and so on. This is how you expand it. Okay, so so that is the idea. Okay, so what you have done here is part of the problem. You know these functions which you have chosen as a basis, but you do not know these numbers. Okay, and these are the numbers which I want to find out depending on the condition which has been imposed on the function. Okay, these are what I meant by having unknown parameters. Okay, so when I write down phi in the function in terms of basis functions having unknown parameters, those unknown parameters are these coefficients. Okay, or how much weights you assign to these different functions, so that when you sum them up, you get the desired function. Okay, so basically, so for example, if you have a function, let's say I have a function known as these 3 points. Okay, and I'm going to write down fx equal to 1. Okay, so let's say this value is my 1 value. This would be my phi 1x. Okay. Then phi 2x x, that is x. Okay. So that would be my phi 2x. Okay. And phi 3x is x squared. That is going to look like a different color. And phi 3x like this. Okay. This would be your phi 3x. Okay. Now these are what is doing. Okay. Now what I'm going to do is at each point. So this point, I know. Suppose the function value has certain value over here. So now, what ratio do I choose? Do I make these combination of red, the blue point, green point, and red point? In certain ratio, I add them up so that I get net value to be this number. Okay, and that ratio remains the same. So at all these 3 points. Okay, so in what ratio do I choose these values so that the net would give me this particular value? Okay, or similarly at this point, what ratio do I choose this 1 and this value, and probably over here this value? Okay, so that I get the net value to be this. In what contribute in what weights do I assign to these points so that I get this number? Okay, and similarly over here. Okay, so that is the basic idea. Okay, so you want to know what is the relative weights assigned to each basis functions, so that when I sum them up, I'll get my desired points, the desired value of the values of the x. Okay, so that is what a1, a0, a1, a2, etc. will be. Okay, all right. So that is the basic idea. So in general, if had I basis on if I knew the basis functions, and let me call them phi k of x. Okay, basis functions are basically a series of functions. Okay, okay, which you might have constructed, or you might have borrowed from somewhere. Okay, but in any way, they are the basis functions. There are certain conditions that has to be met in order to for two fun or a set of functions to be basis functions. There are certain conditions that have to be met. Okay, which is like they have to be orthogonal, and from you remember that when the two directions can be taken as or a bunch of directions can be taken as basis functions, then when you cannot write any of them in terms of the rest of them. Okay, you cannot write any one of them in terms of rest of them. That will be a set of basis functions. For example, in case of x1, x squared, okay, x raised to n, you choose any x raised to p. Okay, I cannot write in terms of rest of the polynomial, rest of the any of those when p is not equal to 1. The pth order x raised to p cannot be written in terms of other linear sum of other rest of the. You have to go. You can always take nonlinear combinations. You can multiply x with x raised to p minus 1, you get x raised to p. But the basis functions are essentially those those functions which, I mean, that set of functions in which any one particular function cannot be written as a linear sum of the rest of the group. Okay, so okay, I hope I have probably clarified on what do you mean the basis function. Okay, and how they are useful. So now, well, so suppose if I knew basis functions, then any function can be written as f of x can be written as ak, okay, where uh, these would be k values. How many values of k would I take? We'll come to that. So it depends on how what are my where are my x points? How many points of x do I have? Okay. All right. You all probably are familiar with Laplace transform. Laplace is like another basis function. Fourier. We'll talk about Fourier a little bit in detail little later. So Fourier is another kind of basis function. Yes, these are sinusoidal functions. The phi k are sinusoidal functions. depending on what you choose your 5Ks, 8Ks will be different. Okay? And which kind of basis function do you choose will depend on the kind of problem that you're looking at. Some basis functions may make it easier if you treat using certain kind of basis function, depending on the nature of problem. It may be easier to handle in one kind of problem, whereas it may be difficult to handle another kind of problem. So that's where your mathematical skill lies. But let's not go into that. This is the most generally saying this is what we'll assume to be correct. Okay. Okay. So if this is the case, now what we are going to do is we are going to talk in terms of a very uh, commonly utilized base set of basis functions. We are going to construct the basis functions now. Okay. So we are going to talk. So we are going to choose phi kx to be something known as cubic spines, B spines. Okay. So that would be the case in this course. But remember, there is no reason that you have to stick to the basis functions. Okay. In fact, the choice of this may not be recommended for certain kind of problems. Okay. So, but what I want to do is I just want to uh, demonstrate how to go ahead with a particular choice of basis functions. Okay. And for that case, I'm going to choose a particular set called B splines. Okay. What are cubic B splines actually? First, let me just tell you that it has a particular shape that looks like a bell. Okay. It's a bell shaped curve, but it's not a single function. Okay. So it is basically not a single function, but number of functions stitched together. Okay. And they are each individual function stitching together, which gives you the given function phi kx. Okay, so R cube. So let me just first write what these things. First of all, it looks like this. Okay, it's a bell shape. But this is not Gaussian. It's not Gaussian. Gaussian is a single function. So what you do here is actually it's not a single function. It's a set of 4 functions. Okay. So what you do is imagine uh, here the point it picks up, so it's basically beyond here it is 0, and it meets at a 0 slope here, and beyond there it is 0. Okay, so here it is beyond this point it is 0, below this point it is 0, above this point 0, and below this point 0. Okay, and then intermediate region is divided into 4 segments. Okay, equal segments. So the 4 equal segments are taken, right? And these segments, these sections, is equal to 1, 2, 3, 4. Okay, they are individual functions. This is one function. This is one function. This is one function. And this is one function. Okay, so they all have. So I can say that let's call these as f1x will be having form like a1x. Sorry, a1. A0 region 1 plus A1 region 1 H plus A1 A2 in region 1 H square plus A3 in region 1 H cube. Okay. This is a third order polynomial cubic function. Okay. Similarly, F2x, this part, so I can probably color it. This part, okay, that will be F2x. That would be A02 plus A1 2 into x plus A2 2 into x square plus A2 A3 into x3. These coefficients are different. Okay, so in this range, something else, some other terms will multiply to achieve the function in the region 2, and then f3 and f4 similarly. Okay, so you have, in general, you have written these four functions in different regions. Okay, and then you stitch them so that they smoothly merge at the boundaries. Okay, smoothly merge at the boundaries. Okay, and the last two functions will be merging to the horizontal line. Okay, with a zero slope. These are the conditions you apply. Okay, so if you just do that exercise, we are not going to do that. All you have to do is like del f1 by del x, del f1. So first, for example, here del f1 by del x will be 0 at this point. Okay, so here I'm going to give a number, give the points here. So this is xk, let's say this is xkth point, that would be xk plus 1, xk plus 2, xk minus 1, xk minus 2. So you say that this is a cubic spline centered at kth point. Okay? A cubic spline centered at kth point. And that is what you call phi k. Okay, so when in this, so basically what you're doing here is now your basis functions look like what? If I just look at this set of basis functions, they look like the following. So what you have here is so this is my x-axis. Okay, I have defined a bunch of intermediate points. Okay, so my first basis function would be looking like so let's say this is equal to 1, 2, 3, 4, etc. And there are n intermediate points, and that would be 1 to n, and that would be n plus 2 here. So that would be n plus 1 and n plus 2. There are n intermediate points. I have n intermediate points and 2 at the boundary, so I have total number of points are n plus 2. If I decide to label it as starting from 1 at the first boundary. Okay, so how do my basis function look like? Y1 would be something like starting over here and picking up over here, and then like this. That is my phi1x. Phi2x, it will start over here and peak at second point, and then go to 0 at fourth point, right? And so on. Something like this. Okay. So this would be my phi1x, this would be my phi2x, this would be my phi3x, etc. Okay. All right. So these are my basis functions. So for example, if I have any function that may look like this, I don't know, some kind of arbitrary shaped function. Okay, some kind of arbitrary shaped function. Okay, so it's up here. Then these. So now at each point you can actually. So you have here and here and here and here. At each point you can basically take the sums of these individual functions. You can take the linear sums and adjust the values. You can assign some weights to these individual functions, okay, which are still unknown, but that's what we want to find out, so that these values actually match, okay, or whatever condition you impose on the function are matched perfectly by uh, giving by assigning some relative weights to these individual basis functions. Okay? So, for example, if the value, for example, just to give an idea, for example, if I'm looking at, say, the function has this much value here, some value, okay. Now, this value will be whatever change I make to, let's say, a basis function, which is this one. Whatever weight I assign to this, I can make it bigger, I can make it smaller. This is not going to affect this point at all. Okay. So any point, for example, this point value will be decided by the weights assigned to only three basis functions. Okay. One would be the basically this one, and this one. Okay, one starting from 2 is already 0 here. So whatever weight I give to this phi 3, okay, phi 4, that is not going to matter at all to this second point. Okay, value at second point. So at any point, essentially, three basis functions, one, so any phi k minus 1 and phi k plus 1 decide, the relative weights will decide the value at any point k. Okay, is that all right? So that is the reason it's little easier to handle. Not all basis functions contribute to a value of the function at a given point. Only limited number, which in this case is 3, contribute to the value of the function at any point. Okay. All right. Okay. Then these are the points. So now so all you need to do is so now wait. So you have basically these conditions imposed on F1, F2, F3, and F4. Similarly, I'll have F3 and F4 also. F3 of X and F4 of X. And what you do is you impose a condition. Okay, impose equality at boundaries. Okay, impose the derivatives to be the same at the boundaries. Okay, so at this boundary, this boundary, this boundary, derivatives have to be the same. Okay, so then you have same derivatives at the boundary. Okay, and of course, function f1 and f4, they go to 0. Okay, they go to 0 at the last points, and the derivatives are also 0. Okay, so these are the conditions you impose on these assumed forms, and that will impose some restrictions on these constants. If you apply these conditions, you will see that these constants can be actually obtained. The question: phi 1 itself contains f1, f2, phi 1. Yeah, absolutely. That's why I'm referring to it as f. So as I said, phi 1 is this entire bell-shaped curve. So I'm trying to answer your question. Phi 1 is entire bell-shaped curve. F's are the individual sections of this. When you stitch them together, this entire thing is called phi 1. Phi. Okay. And it's labeled 1, 2, 3, etc., depending on where it's centered, okay, or where it is peaked. Okay, is that all right? Okay, all right. So okay, so this is our basic idea. So now again, I'm not going to again. So you can do this exercise yourself. You can actually just itself tedious. So you just to have xk minus 2, xk minus 1, xk plus 1, xk plus 2. At each point you, so for example, xk minus 1, you equate f1x equal to f2x. Okay, that will give you, you need to take x equal to xk minus 1 in these numbers. Okay, and then equate these two together. Okay, f1x equal to f2x, f2x to the xk minus 1. That will give you some equation between these unknowns. Okay, so when you apply all these constraints, end of the day you are able to find these equations, these unknowns. Okay, you can check that. You should check that actually. Okay, so please do that exercise and let me know if you are able to, if you are having any difficulty in getting the values of a0, a1, these constants. You can get those values by imposing these conditions. Okay, so end of the day I'm going to get a form that I'm just going to write down. Okay, so I'm going to call basically instead of phi k, I'm going to call them bk's now. Okay, b is for b spline. Okay, so those basis functions I'm going to call bkx. Okay, so bkx happens to have the following form. I have basically here I have actually overall 6 regions. Okay. See if you count the regions beyond the endpoints. Okay, so xk less than equal to xk minus 2. Maybe I can redraw it over here. xk plus 1, k plus 2, k minus 1, k minus 2. Okay, and I have a function that goes like this, and then this. Okay. And this is symmetric actually. We are about that is my dkx. dkx is of course 0 when xk is less than xk minus 2. That is beyond this point. That would be my first case. That means beyond this point, this is always 0. And similarly, when xk is larger than xk plus 2, that is 0. Okay? And then I have regions 1, 2, 3, and 4. Okay? By f1, f2, f3, f4x. So dkx is equal to f1x in this region, f2x in this region, f3x in this region, and f4x in this region. Okay? So, so dkx is equal to f1x, which will have the form. Now this length is equal to h. Okay? We are going to call this. We'll assume that subsequent points are equidistant. Okay? We'll assume that x has been, theta is in equidistant. That's not necessary actually. You can also have not equidistant points. Okay, that's all. That is so that is actually advanced level, little more. There's some difficulty associated, but it solves a special kind of problems. So equidistant. Okay. Set size. So h is my step size. So now I can write down. So if I do that exercise of imposing those particular constraints, I'm going to get these forms. That is region 1. And then region 2 looks a little longer, but well, once I do it, I am done. Okay, so that's why I want you to cross check. Okay? There may be error in this expression. I have made a mistake. So please cross check. So minus 1 by 2h cube x minus 1. So you can like quite couple of things you can directly check. For example, in dkx is f1k. F1k is 0 at xk minus 2. If I put x equal to xk minus 2 here, then this of course becomes 0. Okay, and all of them are third order polynomials. So they have cubic terms. All of them they have cubic terms. Okay, all right. Then other can be obtained by simple symmetry. Okay, by flipping the x about xk. Okay, so I just write that again 1 by 6 minus 1 by 2h x minus xk plus 1 plus 1 by 2h square x minus xk plus 1 square plus 1 by 2h cube x minus xk plus 1 cube. So that will be region 3, and region 4 minus 1 by 6 x cube x minus xk plus 2. Okay, this is what we are going to get for those pi k's x, which we are now decided to call bkx. Okay? So these are my basis functions, and I have given you the form. Okay, so I just want you to cross check it, but presume that this is correct. Now what do I do? Okay, so what do I do next is, so my bkx have been known, and they have certain properties which I want to list down. There are certain important, there's a certain properties which makes life very convenient for us. we can directly use those properties. So the properties of bk. Okay, so if you look at bk, remember my equation. So now, well, remember, okay, I have a question. The different bk, meaning Chandrahas, what is your question again? So let me go back. So bkx are different because xk's will be different, right? Remember, bkx is a function which is centered at xk. That's how it has been labeled. So how we are writing equations to bk? Well, I know that I think I already told that. So bkx has this particular form. Okay, bkx is formed of f1x, f2x, f3x, and f4x, which have these forms. Okay, we do not know these numbers at the moment. Okay, but we presume that they are cubic functions. Okay, f1, f2, f3, f4 will have basically cubic polynomials with different form coefficients. Okay, we want to find these coefficients. How do we find these coefficients? All we need to do is apply the condition that they are stitched smoothly. Okay, which would mean that we impose equality at the bound, at the intersection, the common point where the meet, okay, the joining point, which is x k minus 1 k plus 1. Okay, so here, so for example, f1 will be equal to f2, and at this particular xk minus 1, f1 will be equal to f2. Okay, and similarly k, f2 will be equal to f3, xk plus 1, f3 will be equal to f4. Okay, and then again they do the derivative of the f1 will be the same as derivative of f2 at this point because they join smoothly. Okay, the derivative approach from this side or this side, that should be the same. Similarly, derivative of f2 and f3 will be the same at xk. Derivative of f3 and f4 will be the same as fk plus 1. Those will be the conditions. You say that then you say that these derivatives are 0 as well as the function is 0 at these 2 points. So with those conditions, if you impose, I can find a0, a1, these constants can be found. Okay, that is what I have. That is what I have shown over here. Okay, these are basically nothing. Each f1 and f2, these are basically nothing but those the same form. Basically, these are all the same form. That is a0 plus a1x plus a2x squared plus a3x cubed. They all have this particular form. This one, this one, this one, this one. They all have this particular form. Okay, good. So yeah, there's one more question. Function is basis on find price and basis of degree. Well, you can say that. That's a good observation. You can say that. That's a very good observation. Well, yeah, yeah, you can say that. You can. Well, I think you have got the point. Yes, that's correct, Satvir. Well, to some extent, yes, but I will not take it. I will not use it technically. That's not technically correct, but in terms of ideas, yes, it's correct because the phi is made of f's. Okay, you can think like for phi f's is the f are the basis, and for our own function phi's are the basis. Okay, so is that what you wanted to say, Satvir? Bk has only one value. If you choose x, bk will have a given value. Yes, a given x, bk will have only one value. Okay, all right. Good. So, all right. So now I was talking about the properties, right? Any more questions? I want you to understand it very well, and it's just one example of basis set. Okay, there can be different kinds of basis sets you can construct. Okay, so you can also construct, for example, Gaussian basis functions. You can think of, instead of having these Gaussians have a single basis functions. You can define them to be at different positions, and then everything is looking complex. Well, yeah, this part is I admit this part is complex. I admit, and but thing is that that makes computing very difficult, easy. Okay, see, it's very if you actually cleverly design by giving more by applying more effort, if you cleverly design your method to compute, then you can actually that is well worth doing, because something that can be done in a month can be done in 1 day. If you can speed up a code, if your algorithm is 10 times faster, let's say, okay, then well, the human effort goes only once. Okay, once you devise a method, yeah, you're set, all set. So if that's little bit more effort can save you 10 times computing time. Okay, when you actually compute complex problems. Okay, so something that can be done in 10 days can be done in a day. Okay, something can be done over an entire day can be done in 1 minute. Okay, that is a huge saving. Okay, so that's why it's well worth looking at. So in this course I will, yeah, so I will have examples and methods at least once in a while, which would be sufficiently complex. Okay, and it will be the reason is to challenge yourself. Okay, so just pay attention, you'll be fine. Just understand the basic idea. Don't worry, if you have a question you can stop me anytime. Okay, but we can go slow, that's not a problem for me, but I want you to understand it and know how to use them. Okay, all right, so yeah, don't worry if it's yeah, examples, we'll look at examples, definitely, definitely. I've already given you homework, by the way, and I'm expecting it back by Tuesday. So please do that yourself. And in the meanwhile, if you're having difficulty, you can talk to me, you can email me, you can send me your code which is not working. I can look at them and then I can suggest what was something going wrong or not, what you want, what you can do. You can call me up. Okay. So all right. So examples, I'll do the examples. But yeah, it's this part is a little complex, I admit. Okay, but this is a very important idea I wanted to tell you about this. Okay, so now these BKs that I have constructed, actually this forms a basis of something known as finite element methods. Okay, so finite element methods have also the same kind of basis functions. Okay, so if you, and lot of many of you, especially even chemical engineers or petroleum engineers, will be maybe dealing with finite element methods anytime soon. Okay, so that's another reason I am looking up. I'm basically taking up this particular example, this particular method of this particular kind of basis function. Okay. All right, all right. There's a just to let you know, there's one method called finite difference. There's another thing called finite elements. Okay, FEMs, which are known as. So for FEM, this exposure will be useful. But we will not go into FEM as such in this course. All right. So properties of BK. What is, there are certain properties of BK which, so any function, all whatever the function that I've constructed, which may be centered at kth point. Okay. So that kth point centered function will have the following important properties, which are, I'll just list them down and then we'll finish. So let's say these are my points: xk minus 1, xk, xk plus 1. Okay, and x k plus minus m for m. Xk plus 1, or x, this would be xk plus 2, xk plus 3, or xk minus 2, xk minus 3, and so on. Okay, so these are my points. I'm going to see. I'm going to look at the three quantities: the value of the bk of x, value of the bk prime, the first derivative of x, and value of the second derivative of x at these particular points, these grid points. Okay, these are the grid points. Remember, vk is a function which is defined at a point which is intermediate between grid points. Okay, so vk for any, I can choose any x here, but if I happen to choose those grid point values, then then this is important. I mean, this table actually is corresponding to the BKs at those grid points. Okay, so those numbers I'm going to write down. BKs will be 1 by 6, 2/3, and 1/6. The peak value Vk at xk will be the peak. Okay, Vk will always peak at xk and the peak value is 2/3. Okay, then other values at the next and the two junctions over here. Okay, this point, this is xk, xk minus 1, xk plus 1, xk plus 2, and xk plus 3, etc. And here xk minus 2 and xk minus 3, etc. So here I know that this will be 0. Okay, and there, of course, the derivative, second derivative, they all will be 0. Okay? This point, I can find out this is 2/3. You can just plug in the value. To look at these expressions, just plug in the number. So bk at this point, for example, I have to look at f2, okay, or f3 at xk. Okay, if I look at f2 and plug in x equal to xk, I'll have xk minus 1, that is h. Okay, so 1/2, 1/6 plus 1/2. Just do this algebra, you'll get that answer. Okay, so remember, anyway, xk minus 1, that is equal to h. Okay? So that is the result we can use. Here I'm going to get so derivatives values are minus. So this is obvious because slope here would be exactly the same as slope here, except that would be opposite with the negative sign, right? So slopes would be opposite. Okay, and second derivative will be 1 by will be actually the same, 1 by h square and 1 by h square. Okay, and can anyone tell me what should I write? Looking at this curve, what would go over here? Bk prime at xk, bk prime at xk, and bk prime at xk would be how much? Can anyone tell me quickly? 0, absolutely right. So I wanted to check you're paying attention or not. Okay, so that is 0, and this would be positive or negative. This will be negative and given by minus 2 by x square. Okay, this table will be handy for us when we actually apply this to solve the ODE, the second order ODE that we are planning to do. Okay, all right. So I'll stop here and we'll take it up from tomorrow. Tomorrow we have a class. Yeah. So we'll take it up tomorrow again. Okay. Any question? And if you're having difficulty in coding, etc., you please feel free to let me know. Okay. All right. So any more questions? All right. So I'm going to stop the class.